So it's my pleasure today to talk to you about the chemistry of coffee. To be fair, I'm also probably going to share a little bit of botany and perhaps a little bit of physics. But basically the idea here is that we're going to be exploring factors that contribute to flavor properties of coffee. Now, I'm not going to try and homogenize your preference. In fact, I might validate why some of you like certain things, and I might challenge you to explore new flavors and new brew methods and so forth. And hopefully by the end of this, give you some take-home messages that you can experiment with tomorrow morning. I actually became interested in coffee back in my PhD. I received a PhD from the University of Bath. Bath was actually quite an old city. It was founded in the year 3. This is, some of you may have been. This is the beautiful city of Bath. And Bath itself is known for the Roman baths, which itself is known for its water. It was thought to have therapeutic properties, and it's a topic that we're going to return to a little later on as we think about the chemistry of water and its impact on brewing. Shortly after I finished the PhD, I moved to Boston, so went from Old England to New England, to a relatively old school where I spent 2 years as a postdoc at MIT in both chemistry and chemical engineering. And then I moved to the University of Oregon and started a tenure track position where I had a small research group that studies the chemistry of materials and molecules, and specifically energy transfer within these types of materials. Now, this is an outdated photo, and perhaps I'm missing maybe the most important person in the group in this photo, which is a new PhD student that I have, Robin Bumbaugh, who is beginning a PhD on the chemistry of coffee. So hopefully we will be able to update you with our progress on that, and you'll be seeing or hearing about that in one form or another over the coming years. Now, I got to tell you what I actually am employed to do, okay? I basically try and understand the chemistry of earth-abundant metals. And so I arbitrarily draw this line of ubiquity here, and this is weighted in per million atoms of silicon that you find on Earth's crust. How many of those other atoms do you have? And so basically you see, like, for example, there's 1 million silicon atoms per million silicon atoms, right? Of course. Well, anything above 1 in a million or 1 to 1 million, I'd say, is relatively abundant. Now, in the chemical industry, we typically rely on these rare metals like platinum, iridium, rhodium, and so forth, but they're undoubtedly rare. And so if you could find ways to perform similar chemistry that these elements do, but above this line, then you'd be onto something, because it would be a much more sustainable way of performing catalysis. Now, nature does this, right? Nature has enzymes, and so I've listed a couple on the right-hand side. So one unifying feature between all these is that they use multiple metals. And so one class of materials that uses multiple metals in somewhat of a designer way are these metal organic frameworks. Now, they're basically clusters of metals. In this case, the one on the left here is zirconium with some oxygen around it. The one on the right is zinc. And they're going to be suspended in space with organic molecules. And so this is an example of sort of a honeycomb, sort of a triangular lattice that you'd find in one of the materials that we study. And they're really neat because basically you can perform catalysis with multiple metals much the same as biology can, and target those chemical reactions that you might find in industry by using those earth-abundant metals. Now, we're not here to talk about that. Maybe another time we'll come back and visit you in Kansas City to share more on this, but we're really here to talk about coffee. And for that matter, coffee is a pretty complex topic, and so I must first apologize that if there's something that I don't get to cover in this talk, there's a good chance that there is a recorded one. Here are some links to some of the talks that I've given before. I also want to highlight that actually coffee is a nice plant to grow. And so here, this is my one of my houseplants. This is Jean-Paul. He is much larger now than he was in this photo. And actually, you can find coffee plants pretty easily. Here's a photo of one at Trader Joe's. And if you look closely, you'll see this isn't just one plant in this pot. This looks to be something like 10. So you can go ahead and break these apart, and you can basically grow your own little coffee farm. They also do well in shade, so that's good. Now, in addition to what I'm not going to talk about, I do curate a very small library of peer-reviewed articles on the topic roughly related to coffee. And you can find that on my group website. You can locate that by Googling me at U Oregon, and then navigating to the bottom of the page and clicking coffee literature. And this is just really a potpourri of various different papers vaguely related to coffee. A nice one here from 1979 on the misuse of the word sour and bitter So perhaps you might perceive something and say it's bitter, but indeed you're perceiving sourness and so forth. You get the idea. Very broad range of literature to peruse at your leisure. Now in Bath, this is where my coffee journey begins. I walk into a cafe and I'm presented with a board of coffees. And you can see on the left that obviously these are coffees that are going to be prepared as espresso. And I see then Brazil and some other words that may or may not be familiar, such as the ruby variety and the word natural. And then of course some flavor notes, much the same as you'd find in a fine wine establishment or something like this. And here, this particular Brazilian shot of espresso, I might then perceive fruitcake, brandy, and toasted seeds. But I'm not really sure if I'm perceiving fruitcake, brandy, and toasted seeds because it's from Brazil, or because it's a natural, or because it's the ruby variety, and so forth. And then hopefully then you can really see this is just a sparse matrix of information. And after drinking a lot of coffee and thinking about the data that I'm provided, I begin to piece together what is the relationship between the origin, the processing method, the variety, and so forth, with a perceived flavor experience. But that's, of course, not all that goes into making a cup of coffee. And so let me set the stage for you a different way. That the aim may be to, in this particular cup, achieve the flavor notes of lemon peel, bergamot, and watermelon. Now, whether you like lemon peel, bergamot, and watermelon is independent of the fact that's what this coffee is supposed to taste like. So if you then pay money for it and you then perceive salmiakki, which is a Finnish salted licorice, dirt, and Brussels sprouts, I would say that this is a flavor malfunction. This is something that's gone terribly wrong. And if you zoom out, then it's very easy for us as coffee consumers to blame the barista. However, there are numerous other aspects to producing a cup of coffee that would give rise to that variability, with, in my opinion, the most important being the quality of the green product. In other words, is that crop actually of high quality, low variation between bean to bean, and all the other normal characteristics. Then there's the roast and the water chemistry that's used to brew the coffee. And finally, the equipment is actually not overly important, and we'll discuss that in a couple of slides why that might be. But even then, in between getting the green coffee to brown, there's a whole supply chain where a lot of other variables come into play. Now, it's very easy also to spend the most money on equipment because those are the shiny silver things. And indeed, if you're NASA, you could spend 1.6 million developing a cup that allows astronauts to consume coffee in zero gravity. Basically, this curious shaped cup here, you catch a sphere of coffee or any liquid for that, water-based liquid for that matter, inside the cup, and then that liquid will proceed to wet along this capillary right here and eventually pool at this point where you then would present that to your lips and suck, and you would be able to drink coffee in low gravity. But actually, you don't need to spend 1.6 million to drink coffee, of course. You can just simply do it by grinding coffee and putting it in a cup. And this is quite the reason why I'd say that the equipment is relatively low on the scale of importance, because when all coffee you've ever consumed has gone through this process of cupping, where you basically are making a quantitative assessment of the qualities in the cup by trained tasters. Now, here is 5 cups. They're all the same coffee, just looking for reproducibility between the cup. In other words, how consistent is the crop, and then its flavor characteristics. There's no brew method, really. You just pour hot water on and start tasting it. And then you use a score sheet, and this score sheet is indeed one of the sort of areas of development in the coffee industry. This has been used widely for a long time, but basically specialty coffees or any coffee that scores above 80 points on the score sheet, where you basically have 10 different categories and they sum up for a final score. The lowest score you can get for coffee is 6. The highest score you can get in any given area is a 10. And what I like about the coffee industry is that we all agree that both the best coffee being outstanding and the worst coffee being still good, because in fact all coffee is good, right? So the important point though I want to make on this is that, as we're going to come back to later on, that high scoring coffees indeed value acidity. It's a panel that you must score high in. Now, you may not like acidity, which is great because it means your coffee is going to cost you less money to purchase. And so this panel in particular, as well as a few others that are sort of more difficult to describe over Zoom, such as body and uniformity, those are sorts of things I would have loved for you to experience with me. But acidity is one, perceived acidity is one that's extremely important, okay? So let's see how we get to a high scoring coffee. And it all begins with the agriculture and economics of producing coffee. Now, it turns out that in the US, the coffee industry is worth 1.3% of the US GDP. This is a tremendously large number. It's much larger than most of the chemical problems that we work on in academia. And within the US, the primary method for consuming coffee is what we'd call drip or filter coffee, where you're consuming 1.2 to 1.5% weight per volume, or weight per weight, if you think about water as weighing 1 gram per milliliter. So basically relatively dilute coffee. Espresso beverages are more prevalent in Europe, and they're about 10 times roughly as concentrated, okay? And then in other countries outside of the US, places like Burundi and some of the Central African countries, the coffee industry actually is basically a quarter of their GDP, but almost everybody in the country works in the coffee industry in one form or another, whether it's picking coffee, producing coffee, and so forth. Now, there are two types, two general species of coffee. You've got Robusta and Arabica. Robusta is a variety that's grown, or a species that's grown at low altitude, and you typically find that around the equator. Arabica is grown at high altitude, but the differences don't really stop there. Arabica has twice the number of chromosomes as Robusta, which itself is not a good indication of biological complexity, but it is a good indication that these are really different. They just happen to look the same. The key difference also in Arabica is because it's grown at high altitude, it ripens slower. It has less caffeine, which means it's more susceptible to critters interacting with it in a negative way. And so while we value it, it's also difficult to produce. Now at this stage, this is a roasted bean, but coffee does not grow on the plant roasted, right? It starts out looking somewhat like a cranberry. And then you have to get from the cranberry to the green seed. Now, somewhere in between here is what we call the processing method, where if you were to simply pick the cherry off of the plant when it was ripe and let that dry in the sun, and then somehow remove the husk from the seed, we'd call that the natural process. The pulp process is where you remove the skin, the endo and exocarp, if you like, but leave some of the fruity mucilage intact on the seed, at which point that then dries in the sun and then goes into a fermentation tank to remove some of the residual sugar. And that's called the pulp process, because you physically pulp the bean out of the skin. And then finally, you could wash the coffee, which is where you use water to remove the fruit and the skin. Now, very, very generally speaking, countries that have access to water tend to wash their coffees. Countries that have less access to water tend to process via the natural process. The pulp process is particularly common in Brazil and Costa Rica, where the Costa Rican processing is called the honey process, and in Brazil it's called the pulped natural process. Let me show you, though, that what happens in the sort of a farm situation. Here in bright red, you can see these are freshly picked coffee cherries that have the seeds still within. Now, the one bed to the left is the natural process that's been sitting there for a little longer, and you can see the pigment has started to fade, and these are starting to turn into, you can't see from this distance, but raisins, if you like. And then behind, these are likely washed coffees that are drying out on raised beds. Now, the natural process obviously is a sugary fruit exposed to air. So there's the potential for fungus, bacteria, you name it, to start growing on these beans. And indeed, natural process does yield some defects, some over fermentation-y type flavors, some other unusual things. And these beans that are defective fluoresce. Now, the chromophore, or the fluorophore in this case, that is giving rise to that fluorescence has not been isolated, to the best of my knowledge, by chemists. So there's already an area that we could learn something from. This is while the coffee is green, so I'm not aware of whether it's roasted, you put a black light on, I don't know if they fluoresce or not, I should do the experiment. So at this point then, all the coffee then goes into a fermentation tank just to remove residual sugar on the outside, and basically much the same as chocolate, impart some sort of fermented flavor into the bean. And you might then be thinking, well, how does that stack up to the one you probably are all thinking about? The world's best coffee, allegedly, which is the civet process, where a little animal eats the coffee, removes all of the fruit by turning it into fuel for its body, the seeds then get pooped out into an object that looks exactly like this. Well, it turns out this is not the best coffee in the world, and to my knowledge has never, ever even been close to being ranked the #1 coffee in the world in the given year, simply because it scores poorly on the score sheet. Now, the primary reason is these coffees are not acidic, so you're not going to get any points here, which is going to knock your score down. But also, in my experience with these, they simply look like they taste, and they taste like they look. So there's that. The best coffee in the world, however, does change every year. And I can tell you that there is no particular dependence, but low-scoring coffees are typically those that don't have inherent high acidity. So those are coffees from Brazil, Sumatra, Vietnam, Hawaii, etc. The high-scoring coffees are coffees that do have that and also have very well-defined flavors, those from Panama, Colombia, occasionally Ethiopia, Kenya, and so forth. So at this stage, we've got a green bean. It potentially has good flavors in it. We need to turn it into a brown bean so we can extract from it. So this is where roasting comes into play. Now, the bean starts out at room temperature and it's green. And you drop it into a glorified cement mixer that has active heating. At some point, let's say around 5 minutes, the bean begins to change color to sort of a yellowy tan. And then as you continue to roast, increasing the temperature, you'll hear an audible crack, much the same as popcorn. That is the release of carbon dioxide, water vapor, and so forth. And it's just after first crack is when specialty coffees, or typically light roasted coffees, are then removed from the roasting process. And I've highlighted those in green. So anywhere from where I'd say continue up to about City Plus to full City Plus. At some point, you'll hear an audible second crack. Now that is when you really start to develop really toasty, dark flavors. And those are full City Plus, Vienna, and onwards until you get to a fire hazard, of course. Now, typically then, light roasted coffees, or coffees, let's say, for filter, are roasted lighter, and espresso is roasted darker. But there's no difference between an espresso bean and a coffee bean. They're the same thing. They're just how they arrive at the different colors. And here on the left is a picture of a very large roaster with 3 employees at Starbucks looking bewildered as to how they're going to operate this thing. And then on the right, what we have is a typical roast profile for a given coffee. This was from a coffee roasted locally here in Eugene, Oregon. Now what happens is you're measuring the air temperature. So you're going to drop in room temperature coffee, and the air temperature inside the roaster is going to drop. And at some point, it's going to bottom out there, and that's what we call the soak. Now, the gradient in which you come out of that determines the roast flavors, how much acid and all those other things will be maintained in the coffee by the end of the roast. Roasters look for a variety of different things in this, almost like looking at tea leaves. Basically, they look at the gradient of the temperature to tell them the rate of rise, or in other words, how fast are we getting to hot. But the real thing they care about is the time after first crack, which is what they call development. And the reason is that dark roasted coffee and light roasted coffee are more or less the same process. It's just about how long you have after first crack, so how much development the coffee has. And this is, in general, in the coffee industry, we don't say light and dark. We say more or less developed, much the same as medium rare, rare, and well done for steaks. Okay. Now, scientists have looked at this and said, well, we could take coffee and brew it up like we normally do when we get to the lab in the morning, and then we could take its waste and re-roast it in the presence of zinc chloride under an argon atmosphere at 800 degrees Celsius. That is a highly unusual roasting environment for coffee, but actually in doing so, we gain access to end-doped porous carbon. Now, this is a highly conductive material, and it is known to perform catalysis, in particular, the backwards reaction, rather than water splitting, water formation from oxygen. And this is really important because this is one of the reactions you need for a fuel cell to operate. Now, tying back into my fundamental research, trying to replace platinum, well, presently platinum is the electrode we use to do this reaction efficiently. But it turns out that end-doped porous carbon can do it equal to platinum. So indeed, there may be a use, albeit very energy intensive, to get to this stage for coffee waste in electrocatalysis. Okay, so what the heck's in coffee? It turns out a lot. And this is just 1/4 of the compounds that show up in various different ratios as you're extracting from the coffee and what you end up drinking. And indeed, it is minor fluctuations in these plus all of the other compounds that show up in the coffee that give rise to the various different flavor profiles. And so hopefully you can see then this is quite complex. There's one compound, however, that is extremely important in coffee, and of course that's caffeine. But it's not important because it makes you feel good. It's important because this is actually one compound that, independent of your ability to understand chemistry or whether you're a science denier, we all know that this molecule exists in this natural product. And so that means this is a great starting point for science communication. So I adore caffeine. It doesn't really do anything to me anymore. I'm battle tested. I'm battle hardened over here from this stuff. But basically, caffeine is produced by the plant to protect itself. Okay, and coffee produces it so in a similar way to that of sweet potato, tomato, and other things. And this is a paper which I apologize for. The reference has gone missing. A science paper in 2014 on the biodivergence and the production of coffee, of caffeine in coffee. Now, the most common question then is, well, do different roasts determine different amounts of caffeine in your cup? And then do different brew methods determine different caffeine? And the short answer is that caffeine itself melts as a pure crystal at 235 Celsius. It boils at 178 Celsius, which means this compound sublimes. Now, you may remember that if the compound is impure, then these numbers are going to go down. So basically, in coffee, it's not pure caffeine, it's a variety of molecules. And so, of course, then solid caffeine will be evaporating out the smokestack as you roast your coffee. So in principle, dark roasted coffee should have less caffeine. However, light roasted coffee has less access to the caffeine because you haven't broken down as much of the molecular structure and cellular structure of the bean. And so it turns out it's a wash. Dark and light, they're more or less the same. And then the second thing is that caffeine is not all, it's soluble. You get about 20 grams per liter of caffeine in water at its limit. However, it's relatively slow to dissolve. So drinks that are made quickly tend to have less caffeine than drinks that are made slow. And so an espresso shot tends to have far less caffeine than a cup of coffee. And so I can see here like a double shot, well, you know, 2 tall shots, by the way, is just running espresso for a long time. So that, of course, is going to gain access to the same as a brewed cup. But 2 conventional shots, that gives you 140, and a cup of regular coffee would give you 164. So if you want a bunch of caffeine, generally speaking, people tend to have a cup of filter coffee rather than a shot of espresso. Espresso is just more concentrated. But I'll tell you what, it is mighty difficult to assign a flavor to a molecule. And instead, what we would rather do is have flavor notes, a flavor wheel. And as you can see, it's behind me, and here it is on your screen. These are, this is a lexicon. This is a language that allows you and I to communicate whether we're perceiving the same flavor. So as you go around this wheel, there's standards for how you can taste different things. For example, for peach over here, the reference for peach is sweetened, raw, like not made up Jello powder, peach Jello powder. That, independent of whether we call that a peach, that is the definition of the flavor of peach that we mean when we say peach on this wheel. And so then hopefully you can see that this removes our relationship with the flavor and sort of helps us standardize the detection of that given compound. And this is what the coffee industry tends to use. They try and use the uniform language so that we're all speaking the same flavor notes together. So at this point then, you've got a brown bean that needs to be turned into dust so that we can gain access to all those lovely flavors. And you're somewhere going to start on the left at whole beans and end up somewhere on the right, or maybe even further out the screen to really fine. And this is inherently difficult to discuss then via Zoom, because how fine is fine? And I know some of you will brew at French press, and some of you will brew with an AeroPress and pour over and whatever, and they all need different grind settings. And it's basically impossible for me to tell you how coarse or fine you need to go from Zoom. So instead, what we tend to do in the lab is we use a laser diffraction method where we basically pass particles by a light source, and the light diffracts around these particles and gives you a measurement, a direct measurement of their size. Now, obviously, you're going to grind your coffee some way. And perhaps in question time, we can talk about the differences between these. But the key thing then is you want to have more or less one particle size so that you know that the rate of extraction from each particle is more or less the same. Now, when I did these experiments back as a graduate student, I actually asked the instrument manufacturer if they would lend me one, and they did, and they actually took me to the cafe that I initially showed you that chalkboard from, and they put it in the cafe for a day. So we did a whole bunch of experiments right here in the cafe. And what we got from that was a particle size distribution that looks something like this. So what you see here is the size on a logarithmic scale in micrometers. And then this is the volume percent. So in other words, if I hold some amount of coffee, what volume of it is made up of big pieces, little pieces, and so forth, as well as some other ways of looking at the data up above. And the first and most striking thing is you can see that as we grind finer, so as the numbers get smaller, the big pieces get smaller. And the reason for that is that the burrs in this case are two metal plates, and the grind setting is determined by the gap between the plates. So as you make that gap smaller, the pieces have to be smaller to exit. The other thing you'll note then is that the really small pieces, the dust, the fines as they call them in the industry, don't get smaller, they increase in concentration, or you create more of them. And the reason for that is that every time you break the coffee, you make the dust. The dust can always leave the grinder, doesn't need to be further fractured. And the big pieces need to be further fractured. So as you need to break the big pieces down smaller and smaller, you end up making more and more dust. And so you basically get a relationship that does something like this, okay, where you get big pieces getting smaller and small pieces increasing population. These days, they even make grinders that tell you the distance between the burrs. So that things are getting quite high tech. Now, I once gave this presentation actually at a library, and a maths professor there notified me that this particle size distribution is exactly the same as what you observe for exploding volcanic rock. It gets shot out of a volcano and the air breaks the amorphous rocks into a variety of pieces and follows the same distribution. Now, the one shortcoming in the method on the left is that we assume from laser diffraction a sphere. But if we put coffee under a scanning electron microscope, you actually find that coffee has, well, it doesn't look like a sphere to me. There are some regions that have holes in it. And then if you look at the sort of the peripheral pieces, these pieces are actually definitely not spherical, but dense. And so what we're really looking at here is this big piece coming across there. That one that has holes in it is on the order of hundreds of microns. So going back, that's one of these pieces in the big peak. And then the stuff on the little peripheral stuff is the stuff on the outside. So zooming in, you can see this looks like a conch shell. You get the idea. And this is a really difficult problem for physicists and chemists because we can only think in spheres. You know, basically we're asking the question, how big is this sea urchin? Is it this big, or is it really this big? And of course it is this big. Then, you know, this has all sorts of faceting and the volume is less than the bigger sphere. What laser diffraction is giving us is this big, and sort of an average somewhere in between. And that means that we're going to overestimate the amount of volume contained within the particle and underestimate the surface area. But it's just something we're going to have to live with. And then, as you saw in the previous scanning electron microscope images, as the particles got small, they got less porous. So a spherical approximation is better for them. In an article in 2015, they sort of showed that in some way. But let's just appreciate that this is a complicated measurement to make, and it's difficult to understand the kinetics of extraction for something that is so amorphous. But then when we think about those holes that you saw, well, in chemistry, in those metal organic frameworks that I showed you back at the very beginning, they also have holes, but they're on the size of molecules. The holes in coffee are on the size of, let's say, hundreds of micron, or you know, say 100 micron. And so from a diffusion limitation perspective, big holes don't pose kinetic problems for extraction, not really. And so we can pump a whole bunch of gas into one of these metal organic frameworks and see that this thing uptakes a bunch of gas. So almost 1 milliliter of nitrogen per gram of, 1 liter of nitrogen per gram of MOF, which is a lot, right? It holds a lot of nitrogen. On the other hand, roasted coffee holds something like 9, which is what you'd say is dense. Okay, this is a dense material. So it's not, spherical approximation's reasonable enough. Now, I told you before that you couldn't affect the size of the fines, but it's not 100% true. In fact, if you just look at this, the fines peak is, the number of particles passing by the detector. One way to affect these sizes is by changing the temperature of the beans as you grind them. Now, what we find then is that at room temperature, you get this little hip right here, and generally the particles are bigger. And then as you cool down, you get a more skewed Gaussian type form, and the mode gets smaller and smaller and smaller as we cool to liquid nitrogen temperature. And we can understand this from sort of material science. Basically, at low temperature, cracks tend to propagate, well, at any temperature for that matter, cracks propagate through in between molecules. You're not breaking molecules apart. You're looking for pathways between them. And at low temperature, the molecules aren't moving all that much. And so you basically are thinking, okay, well, the material itself is not going to, you're going to get very well-defined cracks. At high temperature, the molecules are moving around a lot, and so the cracks may meander. So as a result, at high temperature, you tend to get a bigger spread and larger particle sizes. And so one conclusion might be that cracks propagate faster at low temperature, or more importantly, you get a more uniform particle size. The other benefit of cooling down coffee, of course, is that certain chemical reactions go much slower as you cool. And this is sort of a plug for freezing coffee, because basically, if you cool your coffee down, you protect it from the environment that it's in. So in other words, you don't put open coffee next to fish sticks, otherwise what do you think is going to happen? But if you have coffee in an airtight container in the freezer, the staling processes are going to go much, much slower. Now, from the Arrhenius equation, or more importantly, the Eyring equation, a very general rule is that the rate of a reaction doubles for every 10 degrees centigrade that you increase in temperature. So if I cool something from 20 degrees down to -20, the rate of staling is basically going to go 2 times 2 times 2 times 2 slower, so 16 times slower. So basically, storing coffee in a freezer will limit the staling process by about, or prolong its life by 16 times. In addition to the fact that the volatiles, the smells of wonderful coffee, are probably no longer volatile. So many of them are no longer going to escape the bean. And so the summary of this is that freezing coffee in an airtight way is a very positive thing. So much so that when I started talking about this back in 2016, this really caught on. And to a point now where there are several companies all around the world, Proud Mary even mounts their coffee hoppers in a freezer. Several people actually freeze individual doses. And in my coffee lab here at UO, all of my coffee's in these single-use bags. Of course, that's an area we'd like to replace so we could limit our plastic footprint. But even this cafe has a freezer built into the bar because the difference is so significant. So much so that actually I was part of a World Barista Championship with Kyle Ramage, who did a wonderful job. And you can see here he's presenting to the judges particle size distributions from our scientific publication. The flavor difference from grinding frozen coffee versus warm coffee is so significant. This is experiment 1 for you to try, is to cool your coffee down and then grind it and see what happens. Okay, so independent of whether you want to do that or not, you do have to add water. And this is really where I began my interest in coffee, was explaining general chemistry and primarily acid-base chemistry to the coffee industry in a way that was more related to coffee. I'm going to do my best to summarize this for you, and let me see, I guess 3 slides, okay? So slide 1 for water chemistry is basically positively charged minerals, things like magnesium, or positively charged cations that show up in minerals like magnesium and calcium, sodium, potassium, those sorts of things. They like to stick to parts of molecules that have high electron density, negative regions. So magnesium loves water, calcium loves water. And indeed, you can see here's calcium with 6 waters hanging around. They also like molecules that taste good. So you can see here, this is theaflavin, a compound responsible for one of the flavors in black tea that shows up in washed Ethiopian coffees. And so indeed, the idea then, generally speaking, is that if you have high metal content in your water, you're going to be able to extract compounds that have electron-rich motifs, oxygen groups, nitrogen groups hanging off of your scaffold. there's a little bit more to this, so we can answer some questions at the end. But basically, if you don't have those oxygen groups, something like alpha pinene, which is a compound responsible for the flavor in chamomile tea, you're not going to see calcium interact with it. And so it actually, in fact, excludes it. So you've already reached a sort of a crossroads here. The water you might need for coffee is different to the water you might need for tea. And so that's already a problem for a cafe setting. But here's the other problem, is that for every plus you have in the coffee water, you need to have a minus. And by far the most prevalent anions or negatively charged species are chloride, Cl minus, bicarbonate, which is this compound here, HCO3 minus, and to a lesser extent sulfate, SO4 2 minus. There are a few others as well. But bicarbonate is the culprit, because what bicarbonate does is it buffers acids. So basically, if I introduce vinegar to bicarbonate, you've probably all done this experiment. Certainly, if you have children, you'll know this. As you add vinegar to baking soda, it bubbles. And it bubbles because bicarbonate absorbs one of those acidic protons, turning back into carbonic acid, which spontaneously decomposes into carbon dioxide, which makes the bubbles, okay? However, bicarbonate will also react with bases to form carbonate, which then goes on to react with calcium to form limescale. And so indeed, water that is rich in calcium that we want for coffee flavor cannot be rich in bicarbonate, otherwise you're gonna have limescale. In other words, you have hard water. And now I believe that some of you might be extremely familiar with this situation where you get that white crusty material forming, particularly when you boil water. And indeed, hopefully this should validate this. But it'll also explain to you why your coffee won't have acid and will generally taste quite bad, is because bicarbonate is wiping out all of those acids. It's doing its chemical job. Let me show you this in a more schematic way. On the left is the flavor wheel with all of the accessible flavors. Now, not every coffee has all of them, okay? But in principle, you could access them. On the right is the contribution from increasing bicarbonate concentration. And so you can see the carbonate hardness going up and up and up. And I've taken the panels out that would be affected based on this carbonate concentration. Let me zoom in for a second and show you this. This is dramatic. You basically wiped out all the lovely fruit flavors. You leave behind some of the tea, some of the sugary flavors, and some of the spices, okay? So this is bad news if you want to have a high scoring coffee that tastes like, you know, lovely acid. In hard water, it's not possible. But earlier on, I mentioned to you that the lowest scoring coffees, the ones that the coffee industry doesn't necessarily put high monetary value on, are those that scored low because of acid. Brazil, Sumatra, Vietnam, and Hawaii, and naturally processed coffees in general, okay? Well, it turns out that they also happen to be coffees whose flavors do not depend entirely on the water chemistry. So the coffee industry sees tremendous value in these coffees because it means that you could have a wonderful Brazilian coffee at a shop and take it home, and you'll still be able to perceive the chocolate notes, the nutty notes, and maybe even a little bit of the sweet aromatics, something like a lovely buttery biscuit. And so for that reason, these coffees are actually extremely valuable, and very well may be the reason that you enjoy them so much is because they're not ones affected by your variable water. Okay, so at this stage then, we're getting close to the end of the talk because we're now about to talk about brewing. And my group specifically is interested in espresso. But I'm going to try and talk to you generally about brewing coffee, whether it's filter or espresso, by talking about the paradigms in the coffee industry. And so very recently, we had this paper published in Matter just before COVID. So this came out just before. And this did the mainstream media circuit because one of the conclusions was that you could basically use less coffee to make high quality coffee. And a couple of slides will explore how that conclusion came to be and also how the media got this so dramatically wrong. But anyway, initially what we sought to do was develop a mathematical model that helped us predict the extraction of coffee into the cup. And in espresso, the only difference from a mathematical perspective is that we're applying hot, high pressure water through a compacted bed. Now this bed can have particles of big and little pieces, much the same as we saw experimentally. And all of these are tangible metrics. But the one thing that we haven't talked about is how do you quantify what you've extracted? Now, in the coffee industry, they've adopted this Brix type measurement. Now, what this is a measurement of refractive index. And this is widely used in wine. And the reason it works so well in wine is that you start out with 15% sugar water with some other flavors in there, and you monitor it changing from sugar to ethanol over time. At some point, you're going to get to ethanol, and you'll have now, I don't know, let's say 14% alcohol floating around in water, and you've made yourself some wine, okay? But because one molecule is 14% of the concentration, the Brix measurement works extremely well. For coffee, there's thousands of molecules, okay? And so it turns out that you have to zoom out and take a macroscopic average of all the coffee compounds floating around. And then the total concentration, the percentage of coffee mass dissolved in water, is then related by some polynomial, and this has just been arbitrarily fitted to a bunch of data, where there's a relationship between the measured refractive index as well as the temperature that you've measured it at, okay? Well, here's the origin of some problems in the coffee industry, is that total dissolved solids, as we discussed, is the mass dissolved in the liquid. There's one other important feature, which is the extraction yield, which is the mass of coffee that end up dissolved versus the mass of coffee we use. So if I got a 20% extraction yield, that would mean that 20% of the original mass we weighed out is now dissolved in the liquid. And the industry then developed this so-called brew control chart where you have extraction yield, which is this top value, versus total dissolved solids, which is the bottom value, to give you what is so-called an ideal concentration and extraction yield to make tasty coffee. However, at this point, it's worth then revisiting refractive index. Refractive index of pure water at 25 degrees is 1.333. Now, what affects refractive index? It is effective density. So molecules that interact strongly with water, such as sodium and chloride, will be locally very dense. Water will be very close to the sodium, giving rise to large changes in refractive index. As you get progressively closer to something that's not all that soluble, water forms cages around molecules, and as a result, you get lower density of water. And so the change in refractive index is going to be not only proportional to the amount of stuff that's in there, but also the identity of stuff. Let me drive this home in a different way. I could dissolve 5% by mass ethyl acetate in water and get the same change in refractive index as dissolving 1 weight percent sodium chloride. And that's temperature independent. Now, with the temperature playing a role, it's also significant. And so overall, hopefully you can see then the Brix measurement is really not informing you about qualities, but maybe quantity of coffee extracted, not necessarily what's in there. Let me give you one final or two final points on this topic. The simplest experiment one can do is brew coffee at high temperature and monitor the extraction of a molecule you can keep track of, in this case, caffeine. Now at high temperature at 90 degrees, we can brew this for a long time. And if we were to take this to 20 minutes and measure the caffeine, we get about 15 milligrams of caffeine per gram of coffee out. If we use 20 degrees Celsius water, we are only able to access, due to chemical equilibrium constants shifting around based on temperature, we can only get to about 9 milligrams of caffeine per gram of coffee, which means immediately you know that temperature is affecting what you can extract. The other thing is that not all compounds are affected by temperature the same way. So the concentration of caffeic acid, a molecule that shows up in coffee, is extractable independent of the temperature. So as a result, you're going to change the flavor based on using different temperatures of water. The other striking outcome here is that several of you might have had a relationship where you thought cold brew was really strong. Well, it turns out cold brew might be really concentrated, so the TDS might be high, but your ability to have extracted all of the lovely flavors has definitely been limited by the fact that equilibrium constants are against you at low temperature. The other thing is that not all compounds extract at the same rate. So molecules that are really soluble will extract quickly and then rapidly deplete. Whereas molecules that are not that soluble will start to increase in extraction as the coffee gets more wet and hotter and so forth. And so you can see here there's some other dependencies on brew temperature where it's really soluble stuff doesn't really depend on brew temperature and really insoluble stuff does. there's a lot to unpack, but basically what I'm trying to tell you is a refractive index measurement is really not capturing relative differences in populations of flavors in coffee. And so it is one piece of data to tell us how efficiently we've extracted, but it's not everything. And so what my group is doing is developing a novel method to use electrochemistry to monitor the content of molecules in coffee by shoving electrodes in there and passing electricity through the beverage. And it sounds a little crazy, but I assure you it's been done before, perhaps never in a quantitative way to assess qualities of coffee. But basically the reaction is simple. You scan, you increase the voltage, and at some point some molecules will react. Now on this picture here, the secret is this little oxygen atom with this proton is gone, okay? So all that we've done is we've just removed an electron and a proton, and by doing so we're able to detect the quantity of chlorogenic acids. And this really, really works. So if you look at coffees, this is from oh, that's an improper reference. I'm sorry, I should have updated that. But if you look at coffees from various different producers and different companies, you could use high performance liquid chromatography, which is the Rolls Royce, if you like, for monitoring what is dissolved in water. Or you could use our electrochemical method, and you can see the electrochemical method is able to measure chlorogenic acids, the compound I showed on the previous slide, in basically the same resolution with the same confidence as HPLC. So this is really good news because now we're able to monitor a very particular molecule. Whether it's a marker of quality and flavor is ongoing work. Let's go back though to refractive index briefly, because it's all we've got at the moment. Because we only measure a cumulative measurement of extraction, we are then able to parameterize our mathematical model with one diffusivity constant and one rate constant for coffee stuff. How fast does coffee extract? Of course, coffee is more than one compound, but this is what we've got at the moment. And as a result, our model is able to predict the impact of grind setting on extraction yield. So you can see then that if I pass the same amount of water at the same temperature and pressure over our coffee bed in our model, you'll, at 20 grams, as you grind finer, you get more stuff out of your coffee. If you use less coffee, then you get more, you extract more of that extractable mass. If you use more coffee, you extract less. This is pretty intuitive. The one on the right is the effect of pressure. So if you use lower pressure, water is going to move slower through the bed, and so as a result, you're going to end up with more stuff being extracted, and the opposite is true for high pressure. No surprises here. However, if you do this experimentally, our model's in blue, experiment is in gray, these dots. You can see that at some point when you grind too fine, you're no longer able to access all of the coffee. The water is going to find more efficient ways to pass through the bed than trying to trickle through all the little nooks and crannies. And as a result, you become very inefficient in extracting from your coffee bed. And worse is, what if the barista tells you that they liked this grind setting right here? The variability between here and here is tremendous. And more importantly, what is this actually telling us? Well, it's saying it's probably a fraction of the coffee beds extracted to 25% of its mass, a fraction at 24, a fraction at 23, and so on and so forth, all the way to the potential of some of that coffee bed you extracted from may be dry, which means 0% of it was extracted from. And as a result, you're seeing the extraction yield, the average of what we measured from the refractive index, go down. And so this finding was the origin of us saying, oh, we know how to be more efficient in extracting from coffee. If you're wasting coffee, you're not able to access what our model was predicting, why not just grind coarser to get to where you're extracting evenly from all the coffee, and then just use a little less water so you hit the same extraction yield? Makes sense. So the problem here, though, is the beverage is getting smaller. The other alternative is, well, if we know we want high extraction yields, and perhaps this flavor over here on the left is tasting good because a portion of that bed is being extracted at 25%, much higher than what we were measuring. Why not just use less coffee and also still grind coarser? And so one of the easy things to do would be, well, why not just take the same, just use less coffee so that it rigidly gives you a bump up in extraction yield, maybe grind coarser to a point up to this point. Or if you care about only extraction yield, just use less coffee and grind much, much, much coarser and get over onto the reproducible side where there's less variation between shots. Well, here's a problem. Before I told you the top makes smaller beverages, and the bottom one uses less and less coffee. So the conclusion from this is that the most reproducible coffee is one that involves no water and no coffee whatsoever. Well, that's not good, because obviously we all want coffee. And so somewhere in here, you have to make a decision as to what's the smallest drink you're prepared to accept. And at the same time, what's the lowest concentration you're prepared to accept? How dilute do you like it? But the key finding is grinding coarser gives you higher reproducibility. So much so that I actually implemented this in a cafe in Eugene, Oregon, almost 3 years ago now, where instead of using 20 grams, we down dosed to 15 grams. And this doesn't seem like a lot, but if you pull a lot of shots of coffee in a small store, like roughly 30,000 per year in a small store, they save about $3,600 just from going down a little bit. And looking at their Yelp reviews, they got better, okay? Simply because it was reproducible. Now, if you were in a cafe like a big Starbucks or something and they were doing 500 drinks a day, that saves each cafe $24,000. And an estimate that we made when we wrote this paper was that if every cafe in the United States were to down dose and more efficiently extract from their coffee, that would save the United States $300 million a year, simply just from being more efficient dialing in their espresso. So hopefully you can see there's tangible real world impact in this. But let me leave you with a couple of thoughts and take-home messages, some actionable information. That in all of this, espresso became complicated because somewhere along the line, we borrowed some language from the Italians, then Starbucks changed some words to mean different things, and now we have a single and a double espresso, and it's not really clear what they mean. But basically, a single espresso, in my mind, is one process of making espresso. However, the original definition of espresso was determined by the volume. And so if you make a large shot of espresso and split it in half, then you might call each of those a single. Together, they may be called a double. You get it, it's complicated. What you really should be asking when you're thinking about a single versus a double is really how much coffee did they use to how much water did they push through the coffee? In other words, the brew ratio. That really is what determines the concentration. It determines all those other factors that we were talking about before. And as a result, then, when you think about espresso drinks and the volume of the espresso plus its concentration being important, what really then is important when you're thinking about milk-based drinks is the ratios. And this, hopefully, you already paint the picture for yourself that espresso, of course, has no milk. And as you build up in brew ratio 1:1, macchiato 1:2, cortado, all the way up to a latte, which is 1:5 or beyond, this is all going to be governed by how much espresso you had in there in the first place, as well as its concentration, not the cup size. And, you know, this is outside my jurisdiction, but I can tell you for sure, this has been the origin of many problems in the industry. It's just making sure we speak the same language. The second conclusion here is that the shot time, a metric that sometimes we might monitor, is actually a dependent variable. It depends on grind size, water pressure, all these other things. And so what actually really matters is reproducible flavor. And to achieve that, you need to basically control mass of coffee, mass of water, and then you're going to be monitoring the flavor based on the brew ratio. All right. Finally, you might walk away from this thinking, well, I really will now know that cold brew is less efficient than hot brew for accessing flavors, and that is definitely true. Yet we don't yet have a method to quantify that. And so that is what my group is working on, and I hope in the very near future that you will be able to walk into a cafe and have a barista with a potentiostat measuring a cyclic voltammogram of an espresso shot for you to ensure that you are getting the flavor that they intended. Now I'm going to leave you with two more slides. The first is, these are some people, but not all, that have contributed to all the work that I've done in coffee over the years. Most of it is charitable contributions, academics with shared interests, roasters with a view that they want to improve coffee for everybody, not just for their business, and baristas that have, you know, dedicated their time and expertise to basically helping teach me coffee while I taught them science. I also want to leave you with some actionable information. First of all, the brew recipe is the most important thing. A good starting point is 60 grams per liter. That is 60 grams of coffee per liter of water you use. And you should be weighing your coffee and you should be weighing your water. So you actually can figure this all out and figure out what tastes good and what doesn't. And then very roughly, these are some grind setting, but they don't, hard to know what that means. The next thing is water chemistry matters a lot. Now you may be motivated to brew up your own water by starting with deionized water and buying these Epsom salt and baking soda and putting it all together and away you go. Alternatively, go buy Evian water and have a bad experience. It's very hard. Go buy Dasani and have a much better experience if you like acid. It's very soft. And somewhere in between, you'll be able to start to understand the impact that water has on flavor of coffee. And finally, you've heard me preach about acidity being very important. It's only important if you like it. It's important in the industry. And so if you want to try one of these coffees that is acidic, take some soft water and brew up a Kenyan coffee, and as well as Central Americans as well. Colombians can be very acidic. And if you want to try a low acid coffee so you can understand what one of these lower perceived acidity coffees are, you've heard me talk about those all day. Now, I don't have any affiliation with any shops in Kansas City, but I can tell you for sure that you've got plenty of places you can go into and try a single origin brew at Post Coffee, Messenger Coffee, Monarch Coffee, The Roastery, all of these places and more. Anytime you're traveling and you want to try a good coffee, go to sprudge.com and search the city you're in. I guarantee they've written an article about specialty shops in your area. But with that, I want to most importantly thank you all for your attendance. I look forward to answering all these wonderful questions that you've got in the chat window. And I hope that you and your families remain safe as we hopefully get to the end of this, this tough couple of years. Thank you very much, Eric, for the invitation as well.
Well, thank you, Dr. Hendon. That was some great information. And I'm so glad, for one thing, I'm glad to hear that freezing the coffee beans is a good thing. That's what we do. And I was kind of a little anxious there when you started talking about it, but it turns out to be a good thing. So at least here in our household, we're on the right track. I know we're approaching the top of the hour, but Dr. Hendon will be able to stick around for a few minutes to answer questions. Let me start. There was one question asking if Dr. Hendon can send us a copy of his presentation.
Absolutely.
Well, rather than that, though, we'll have a recording of this presentation posted on the Linda Hall Library's website and on the library's Facebook page.
Great.
And we can just smoke through these questions here. Are there genetic differences in taste for humans in coffee taste?
Yeah, so in other words, I assume that this is talking about the genetic difference between you and I rather than the coffee itself. But
right.
So first of all, there are definitely genetic differences in taste in the coffee itself. But then between you and I alluded to this early on, that the flavor wheel that's behind me is used to standardize our way of describing flavors. It doesn't standardize our way of perceiving them. And indeed, I have a test that we can do to see whether you're able to perceive extreme bitterness. You and I may be very different in what we can taste. What's more important than identifying differences between you and I, because I think at this stage in the world, we should be looking at the similarities between you and I rather than the differences. But most importantly is that even if you're perceiving a flavor you don't like, to tell me what you're perceiving is more important than the fact that you don't like it. So that the next time that I would be able to brew a cup of coffee for you, I would know that I'm perceiving that flavor you don't like. I'm going to not brew a cup that has that particular flavor in it. And so while you and I may actually be different genetically, almost certainly, you're not my twin, so we definitely have differences. We're not as different, at least from the trained panels of tasters. We're not as different as you might think.
Here's a history of coffee question. How did people, centuries ago, how did people originally figure out how to process coffee beans to produce drinkable coffee?
Yeah,
or is that an unknown, really?
I know. So coffee's birthplace is Yemen and Ethiopia, in that area. And there's been ceremonial aspects to this as well. The person who first roasted the bean on a pan, or however they did this, I don't even know how they managed to do this. and decided to consume it is beyond me, but something that I'd encourage you to look up Professor Diana Garvin here at University of Oregon, who's in Romance languages and has a very fond interest of the history of coffee. But more generally speaking, just anybody who ever was the first to try anything that they ate is a very interesting. I mean, who's the first person to try a mushroom? You know, that is, something.
And depending on the mushroom, it may not have been around a long time.
Oh, don't eat that one. Yeah, that's.
There's a question here about, where's the best place to keep coffee once it is the freezer, right? And
yeah, so look, here's the thing. As soon as you grind that coffee, the surface area goes way up. And as soon as that happens, you're going to lose all the volatiles really quick. So the very first thing is whole beans is the best way to keep coffee. Now, whole beans on the counter or in the freezer is way better than having pre-ground coffee. But I do understand that pre-ground coffee has obvious upsides. And if you have pre-ground coffee, the surface area for gases to leave is also the same surface area for stuff to go in. So having pre-ground coffee stored in a freezer in a non-airtight container, and I don't mean like just a jar, I mean like a vacuum sealed situation, you're really exposing yourself to that coffee every time you open it, absorbing a bunch of stuff you don't want it to be absorbing. And so honestly, if you've got pre-ground coffee, I would just try and get through it and only buy as much as you need so it's still fresh, so maybe once a week or something. But by far the best way to store coffee is in an airtight container in a freezer. I see, Eric, just to look briefly at the chat.
Yeah, go ahead. Yep.
Yeah, so I see someone here asking about, is it better to drink cold coffee? It's the temperature I'm referring to is just the storage of the beans. And I suspect this question may be rooted in that graph that I showed of caffeine showing up in lower concentration in coffee that's been brewed cold. If you're worried about caffeine uptake, then I would consider only drinking cold brewed coffee. However, it's not clear to me that the amount of caffeine that you get from one cup of coffee is necessarily a health risk, and an argument that shows up from time to time in the media and so forth. And then just to go down below that about reheating coffee, is it unhealthy? It's not unhealthy. It just doesn't taste that good, because all the volatiles are leaving the cup. So if it's gone to cold and then you reheat it, you're going to give it even more time to lose stuff. It's just not going to be the same.
Who decided the flavor profiles? How was that put together? Do you know the history of that?
Yeah, so actually, come to think of it, I believe that this flavor wheel very first was constructed at Kansas State. So not far from you guys. Well, a little far, but not too far. So it was first identified by panelists as a lexicon, like flavors that people just identified. And then it went to a few other schools. Texas A&M had their fingers in this pie, and then at some point UC Davis, basically all the ag schools. And they did some sensory and then some statistical analyses to group these together. There's problems with it. It's not the only way of describing coffee, and many roasters don't use that same lexicon. But it is a nice tool that puts us in the ballpark of being able to speak the same language. So there is science behind it. It's a 2016 paper, and you can find that on my library on my website.
I'll have to check that out. Yeah, Kansas State's in the neighborhood here. Kansas, yeah. Down the road west of us. I think you probably answered this question about chemical compounds in a cup of coffee.
Yeah, that's a great question. I mean, there's thousands. So it's something like 2,000. The reason it's so high compared to other drinks is that when you roast something, you're generating a lot of a new chemistry that was, derivative from what was in the bean. Those reactions are extremely complex, very difficult to control. And so as a result, you're generating a lot of stuff. And then what dissolves in water is yet another consideration, but about, a couple thousand.
We have a question about the sense of smell in coffee, and this kind of a biomedical question. Do you know?
Yeah, I see that question there. So much the same as in wine. the idea of volatile acidity and basically any volatile compound, one that has a boiling point lower than the room temperature or the temperature of your mouth, is one that you're going to be able to perceive retronasally, but also one that you can perhaps detect on your tongue. But generally speaking, your olfactory system, right? You can there's two ways to get in there. There's one through the nose and one through the back of the throat. In terms of how people are perceiving coffee that have COVID, that is, or even post-COVID, I actually did not see that article. So if that is something that you are aware of, can you send that to me in an email? Because that is very, very interesting. It's an area that I'm working on getting funded from the National Institute of Health, is this idea of basically having altered sense of smell and taste, not necessarily from COVID, but just from people who have had cancer and had chemotherapy. Sometimes that happens. I'm curious about that, how we're rewiring, right? Something like rewiring in your olfactory system. But I'm interested.
What's your email, Dr.?
My email is, let me see, I'll go to the front page here and we'll get it up there. There it is, right there at the bottom.
All right.
Yeah, I see another question here. You expose coffee grounds 90 degrees Celsius, hot water, 5 minutes, get good extraction. But if I forget and the coffee cools before filtering, will the compound stay in solution or reabsorb? Some compounds can reabsorb, but actually, as it turns out, almost all of that extraction is governed by entropy, which is the propensity for molecules to become more disordered. And so for a molecule to go from solvated to solid to stuck in a matrix or deposited on the matrix is actually strongly disfavored by the universe. And so generally speaking, unless you're above the solubility limit, which you almost never are, compounds will not go back into coffee. But what may happen is over a long period of time, you might get enough of a population of a slowly soluble compound that as a result, you start tasting flavors that were never intended to be extracted, or at least the roaster never quality controlled for them. So you're sort of out in the Wild West, if you like, if you brew for really long periods of time.
There's a comment that HCG alters coffee smell as well.
Yeah. Yep.
And these flavors in coffee, are we talking literal or metaphorical?
Yeah, you know that, Edison, that's a fabulous question. Okay, so you know on this flavor wheel, and I showed you the impact of water, and it was like being altered. You know, all these panels were sort of fading in and out on this particular slide. The way I constructed this was I took the natural products. For example, in lemon, you have limonene and you have citric acid and all those things. And I noted whether the natural product molecules were affected by bicarbonate, which is a logical leap from, does coffee have limonene and citric acid and all those other compounds that make us say lemon, when in actual fact it may not be the same compounds? And the answer to your question then is, we are speaking in a relationship with the flavor, not necessarily the same molecules as the flavor. And so actually this picture I have drawn here is really an approximation, because who's to say that the molecules in strawberry are the same molecules that are in a strawberry tasting coffee? They're more reminiscent of them. I see Mark has asked a question about, does coffee prevent illness?
And we hear about that all the time. It prevents or causes illnesses. So
basically, the short answer to this question is, you're going to see arguments for and against causing for positives of health and negatives of health for anything in the human diet that is consumed as widely as coffee. An example of which would be antioxidants. This is a class of molecules that basically would prefer to react with oxygen in the air rather than you reacting with oxygen in the air. In other words, you've given your body sacrificial molecules that are going to stale or age rather than you. Are they beneficial for health? It's a back and forth. People always say antioxidants are beneficial. I suppose it is. I'm not an expert in that area. On the other hand, any product that's been roasted generates molecules that in principle could cause cancer if you had enough of them, because these organic flat carbony things, they they can affect the way your body works. And there's acrylamide, which is another molecule that is generated when you roast natural products that can contain amino acids. But it's all about the amount you have. Basically, you can kill yourself drinking too much coffee. Caffeine will poison you and you will die. But a little bit of caffeine will make you feel great. And so somewhere in between there it's a tough balance. But it's everything in moderation when it comes to chemistry. That's for sure.
And that's true with a lot of things in life. Dr. Hendon, thank you so much again for taking the time to share your expertise. We all love coffee, so this was just right up my wheelhouse, and I'm sure our attendees felt the same way. Dave on Facebook commented how much he appreciated the presentation.
Thank you, Dave.
There's a comment. Stephen in chat writes, very informative and interesting presentation, and he's looking forward to rewatching the recording. And again, the recording will be available now immediately after the program on the Linda Hall Library's Facebook page, and we'll have a recording also up on the Linda Hall Library's website, probably tomorrow. So Dr. Hendon, yeah, thank you again. We'll have to do this in person sometime in Kansas City.
Yeah, I'll tell you what, if we can do it in person, we'll make sure we have coffee tasting alongside so we can really go through those flavors. And I look forward to that.
I vote for that. I'm up for coffee anytime. And thank you everyone for attending today's program. For more information about upcoming events at both the Kansas City Public Library and the Linda Hall Library, visit kclibrary.org and lindahall.org. When visiting our websites, I hope that you also take the opportunity to support the libraries through our foundations. Your contributions help make all of our programs possible and freely available. So thank you again, everyone, and have a great rest of your day.